Okay. So either you have this equation memorized, that is the molar volume is equal to RT over P. You can figure it out by units. You got to make sure the units have to come out to what? Liters per mole. Okay, the thing is, you know, if you memorize this and you get it wrong, the units are going to come out wrong. Or you know how to derive it. Either way is okay. But the pressure, you know, is going to be in the wrong units here. And so what we have to do is we'll have to convert from torr to atmospheres. And the conversion here is 760 torr, which is, the torr is the same as millimeter mercury. So this could be 1.10 millimeters mercury or 110 torr. And so actually it's pretty small, the pressure is. Let's see what the pressure is. That's 1.1 divided by 760. 0.001447 atmospheres. It's like 1/1000th of an atmosphere. Pretty small pressure. Well, if the pressure is very small, what happens is the gas expands quite a lot. You know, high pressure, the gas gets compressed. Low pressure, the gas expands. So the volume is going to be kind of big, you know, I would think. And so we'll just plug it in here. So the molar volume is equal to R, 0.08206 liters times atmosphere per mole Kelvin, times T, 303 Kelvin, divided by P, 0.001447 atmospheres. So the units, atmospheres canceled, Kelvin cancels, liters per mole. We could have done the conversions, like the book does the conversions inside the equation itself. You could do that as well. In fact, it's preferred for minimizing round-off error. However, I did it separately. And so I still have this number in my calculator, so I'm going to invert it. Times 0.08206 times 303. 17,178.8 liters per mole. I don't have a box that big though. And so you take 1 mole of gas here at 1 atmosphere pressure. 1 atmosphere pressure, although this is 0 degrees C. And then you lower the pressure, what happens to that gas? That gas is going to expand to from 20, 23, 24, 25 liters to 17,000 liters. It's still the same 1 mole, 6.022 times 10 to the 23rd molecules. Does that make sense? For that? And so both these gases, helium and neon, will have the same volume, you know, at that, under those conditions. It just depends on the number of particles, molecules. In this case, atoms. Helium and neon both are individual atoms. Does that answer the question?
Yeah, it does. So we just have to find that value. I thought we had to compare the neon.
Well, the comparison would be like this. So we have a gigantic box. And so helium, if you want a comparison, this would be 6.022 times 10 to the 23rd atoms of helium. The size, the volume of this box is 17,000 liters. 17.1 times 10 to the 3rd liters. Kiloliters, people don't really say, but 17.1, 17. And then in weight, how much would this weigh? This would weigh 4 grams, because a mole of helium weighs 4 grams. The box would weigh 4 grams, gigantic box. Now, if we have neon in here, then it's going to be the same thing. It's going to be 6.022 times 10 to the 23rd atoms of neon. And that many particles is going to occupy the exact same volume. The volume depends on how many particles we have, either molecules or atoms or what. And so it's going to be 17.1 times 10 to the third liters, or 17,100 liters. But it's going to weigh a different amount. This box is going to be heavier because neon's heavier, the atoms are heavier. It's going to weigh about 20 grams. Therefore, this is going to be more dense. This is going to be less dense, but the volume is going to be the same. The volume just depends on how many gas particles we have in there. That's why, like a mole of air is going to occupy the same volume under these conditions. I could have a mole of air. It's a mixture of gases, same volume. It's just a mole of air would have a total number of particles, 6.022 times 10 to the 23rd.
So because it's such a low pressure, it occupies such a large space.
Yeah. So what did they do? They just calculated molar volume and just said the molar volume doesn't matter what the gas is. It's going to be the same. The density will change, however, and the weight will change depending on what the gas is. But the molar volume doesn't change.
On the text with the conversions, like between bar, is that a given? Or?
Yeah, that's a given. This one you should know, but 760 millimeters of mercury or torr per atmosphere. You should know. Okay, other questions? Where did we leave off? Finished 29. So let's take a look at another gas problem here. 31. The reaction used to produce chlorine in the laboratory is there's 2 KMnO4 plus 16 HCl plus 2 yields 2 MnCl2, 5 CL2, 8 H2O is 2 KCl. Calculate the mass in grams of potassium permanganate KMnO4 that are needed to produce 9.81 liters of chlorine measured for system heat. So this one's not that realistic because if you're going to generate chlorine, you don't want to do it at STP. You want to do it at whatever the room temperature is. And so this is trying to generate chlorine in a freezer box. And so for this one, it's just another gas stoichiometry problem. So let's take a look at how we do this one, or just set it up, how we would set it up. So here we got 2 KMnO4s plus 16 HCl yields 2 MnCl2 plus 5 Cl2 plus 8 H2O plus 2 KCl. And so chlorine's a gas. And so what we want is 9.81 liters of the gas, Cl2 gas. And then we're going to go liters to moles. We have 2 choices for going liters to moles. What are the 2 choices? One, we could use the ideal gas law. N equals PV over RT. So we need the pressure, which we'd have. We need the volume, which we have, that's given. And we need the temperature, which is given. And then we can calculate the moles. Or 2, we can use the molar volume. No, molar volume at STP. STP is not that useful. So let's say we did 9.81 liters. I'm going to change this problem a little bit at room temperature and room pressure. Room temperature we're going to call 298 Kelvin. Room pressure, which one should we use? Atmosphere or bar? Atmosphere? Okay, if we use 1 atmosphere, then the molar volume, you could have this one memorized. What is the molar volume? 298 Kelvin and 1 atmosphere. It's not 22.4 liters, it's 24.5. So this is 24.5 liters per mole, or we can calculate it. It's just RT over P. This is 298 Kelvin and 1 atmosphere, or it's equal to 24.8 liters per mole at 298 Kelvin and 1 bar. The 1 bar is slightly less pressure. Slightly less pressure means that the gas expands a little bit by like 0.3 liters, 300 milliliters. Okay, so we can use, one of these, and like, for example, if it's the temperature and the pressure is one of these, then it's easy, if we know the number. If it's not one of these, then we'll calculate it. If it's not one of these, then the molar volume is equal to RT over P. Then we can use that as a conversion factor, get the moles of chlorine, and then go to moles of KMnO4. For moles of KMnO4, we'll just go to grams of KMnO4 using the molar mass. That's what we want. The moles?
Yeah, we did the 24.5 versus 24.
Yeah, they are two different ones. What's the difference between the two? One is for, and the other is for bar. It's like, we have to do two of them now because, it's like the metric and inch, we have to do two. And so this is kind of the same thing. Lots of people still use atmospheres. Right? Atmospheres is still very popular. In the 1 atmosphere. But now, there's a push to this metric thing, the bar. It's not really, bar is defined differently. Bar is defined from basic physics. But your book loves STP. Chem 1A book doesn't love STP like your book does. In Chem 1A, they're going to take other temperatures and pressures. But look at this. This is 0 degrees C in 1 atmosphere. That's old STP. This is new STP. That's old STP. New STP is 1 bar. Old STP is 1 atmosphere. And so when we look at this, like I said, I had to memorize old STP. Old STP is 22.4 liters. That's like that box there. This is the new STP that people are memorizing, 22.7 liters. But how many people work in a laboratory that's 0 degrees Celsius? Do you know anybody? No. So it's not that useful. All right, here is a case where we're going to have to calculate the molar volume or use the ideal gas law. But how many liters of SO2, SO2 is the product, are produced from 598 grams of FeS2? FeS2 is kind of a weird compound. FeS2, it's weird in the sense that FeS2, some people might know. If you're a geology person, you would know what FeS2 is. FeS2 is called pyrite or fool's gold. This is fool's gold. But, we want to name it. How would you name it, FeS2? Ferrous sulfide? Ferric sulfide? Iron 2 sulfide? Iron 2 sulfide is, iron 2 is Fe2 plus and sulfide is S2 minus. So it cannot be iron 2 sulfide because charges don't cancel each other out. Iron 2 sulfide is FeS. That's iron 2 sulfide. FeS. So if we're dealing with sulfide, what's the charge on iron? 4. This has got to be iron 4 sulfide. Iron 4, is that common? No, not at all. And so what this is this is a special ion. You know, it's one I haven't talked about. This ion's called the S2 2-. It looks like peroxide, right? But it's a lot more stable than peroxide. And so it's a peroxide-like. This is called the disulfide ion. And so this is called iron 2 disulfide, or just a lot of people call it iron disulfide. It's iron 2 disulfide. And so iron 2 is correct, except it's not sulfide, it's a disulfide ion. And so it's a bit tricky, like peroxides. How many liters of SO2 measured at 983? Okay. So, in this case, we calculate the molar volume. Or we use ideal gas law. So here, we go FeS2, we got 4 FeS2s plus 11 O2s yields 2 Fe2O3 plus 8 SO2 is a gas. So we're going to go from grams of iron to disulfide to moles of iron to disulfide. Moles of iron to disulfide to moles of SO2. And then moles of SO2, we're going to go to the volume of SO2 gas by either using the ideal gas law, V equals nRT over P. So we need the moles here. We need the temperature. The temperature is given 214 Celsius. We convert that to Kelvin. And the pressure is given in torr. We convert that to atmospheres. Or we would use the molar volume. So the molar volume we have to calculate. It's not one we have memorized. So we'd end up calculating. Okay. So most of these problems are very similar. So all these look kind of similar. Except number 39 looks different, you know. Like if you look at 38, let's see, how many grams of iron are required to react completely with 5.49 liters of oxygen gas? And so here we just go from liters of oxygen gas to moles of oxygen gas using ideal gas law or the molar volume. Then the moles of oxygen gas to moles of iron, and the moles of iron to grams of iron. So very similar, just stoichiometry. 39 is a bit different because when properly detonated, ammonium nitrate explodes violently, releasing hot gases. So here's ammonium nitrate solid. It's going to nitrous oxide gas and water gas, H2O gas. If the total volume of gas produced, both dinitrogen monoxide and steam, is 82.3 liters at 447 degrees C and 896 torr, how many grams of ammonium nitrate exploded? So now this is a different problem. Do you see that? Here. And so how would we do that? Well, bit of a challenging problem. We got ammonium nitrate, solid. This is going to go to nitrous oxide, gas, plus 2H2O. Yeah. Ammonium nitrate can decompose into different products depending on the conditions of the explosion. what we have is this. We have the total volume of gas. And so the total volume of gas is equal to, the total volume of gas is going to equal the volume of nitrous oxide that's produced, plus the volume of the H2O steam, the gas, yes, water that's produced. And we have that. Total volume is 82.3 liters. 82.3 liters. Now, we're going to use Avogadro's law to kind of figure this out. How much of that 82.3 liters is nitrous oxide and how much of it is steam? And so this goes back to Max's earlier question about the neon versus the helium. In this case, we don't really worry about that here. What we don't know is, we know just the total. We don't know the individual, but we do know something, and that is for every 1 liter of nitrous oxide, how many liters of steam do I produce? 2. For every 24.5 liters of nitrous oxide, how many liters of water? Well, double that. And so it's going to be produced in a 2-to-1 ratio or 1-to-2 ratio. Do you see that? And so we can figure out how much by doing a system of equations. That is, actually, in this case, we can just boil it down to one unknown. And what we're going to do is this. We don't know what the volume of nitrous is, and we don't know what the volume of water is, but they have to satisfy this relationship. And the relationship is, there are different ways we can do this relationship. One way is we can just call one x, the other 2x. That is, the volume of the H2O is going to equal 2 times the volume of nitrous. No, sorry, not nitrous. It's going to equal 2 times the volume of, actually, let's not do that. Let's do it this way. The volume of nitrous, the volume of H2O is going to equal, let's leave it that way, 2 times the volume of nitrous. And so if I produce 1 liter of nitrous oxide, I'm going to produce 2 liters of H2O, right? 2-to-1 ratio. And then let's call that, the volume of nitrous oxide, let's have that equal X. And so what I'm going to do is I'm going to do this. I'm going to just do 82.3 liters is equal to X plus 2X. This is the volume of nitrous. This is the volume of water. In other words, this is going to equal 3X. And then X equals 82.3 liters divided by 3. Okay, and let's solve for X. .3 divided by 3, 27.4. 27.43 liters. So that means the volume of nitrous is 27.43 liters, And then the volume of water is double that, so times 2, 54.86 liters. And if I add both of those up, I'm going to get 82.3 liters. Does that make sense? So we had to do some additional work to figure this out. Okay, now once we have that, then we can just do this. You know, we could just go like this. So we could just take the volume, 27.43 liters of nitrous oxide, and then just go to moles of nitrous to moles of ammonium nitrate, and then moles of ammonium nitrate to grams of ammonium nitrate. Or we could pick water. We can go from 54.86 liters of steam to moles of steam to moles of ammonium nitrate to grams. They both should give us the same answer. You see that? So we just pick one or the other because they were made in a stoichiometric ratio. Okay? With this?